really cover a few more things, which is actually essential if you are going to know a bit about error correction here. Previously, what we saw last time was we saw shortcode, and in particular, we very explicitly saw how to correct for bit flip error only, um, construct the circuit for it and everything. And we also constructed stabilizers for that. We saw that it is very easy to tweak the bit flip error code, and instead of just encoding it into 000 plus 111, we can just encode it as plus 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 and minus minus minus, and that will correct phase flip errors. What we saw, what is one of the most important things here, what we saw is that any unitary matrix which can be an error operator, we can always write it down like a decomposition into the Pauli gates or the Pauli operators. And the way we corrected for bit flip error, the same thing holds for any unitary operator, because we can write it down like this as a combination of I, X, Y, and Z. And when we have the syndrome bits, that syndrome bits gets entangled with the system. And when we do the syndrome extraction, the syndrome bits gets in a superposition in such a way that for each error, it has the corresponding syndrome. And when we measure, the system collapses. And since it's an entangled state, if the syndrome collapses saying that there is an X error, the actual system of interest also collapses into having an X error. If it collapses by saying that it has a Y error, the actual the actual state also has Y error. So that's how we can just take any arbitrary unitary error, and we can just bring it down into correcting the Pauli errors. Also, what we understood is here, y is essentially just z and x together. So if we can correct for x error and z error, and if we do this sequentially, we also correct for y errors. So this gave us our first error correcting code, which was the 9-qubit code or the short code. And it was taking a 1-qubit information and mapping it into 9 qubits. It is able to correct only one error. So it is something that we can call as any error correcting code is given by this NKD. And if we write it like this, it usually means classical. Just to say that it is quantum, when we come to quantum error correcting codes, we write it with this double bracket here. This double bracket implies that it is quantum. Here for short code, n is equal to 9 because, and k is equal to 1, because I am taking a information of a single qubit, which is alpha 0 plus beta 1, and I am mapping it into 9 qubits. So the redundancy is basically 9 to 1. And D is defined the same way it is defined classically. D is essentially, if I can correct T errors, then D is 2T plus 1 in some sense. Here I am able to correct a single error, therefore distance is 3. This is for short code. This is for short code. And we also saw the stabilizer formulation of the short code. We saw the equivalence between the syndrome picture that we have seen versus the stabilizer picture that we have discussed, and we also discussed the stabilizers of the short code and what they essentially mean here. You can very easily check from this that it is only able to correct a single error. Let's assume there is an X error. Okay, so if there is an X error in, sorry, if there is an X error in any of these three chunks, a single X error will anti-commute with any of these, and therefore we will have a negative sign in the stabilizer. If there are two X errors, so let's say that I only have a single X error, I'm taking this x, don't take this as a stabilizer, just showing you the x thing. Let's say x error occurs on the first qubit. So it will not anti-commute with S2 because it has an identity on qubit 1, but it will an anti-commute with S1, and therefore it will give a -1 eigenvalue. But it's easy to see that, say, if I have x like this, it will anti-commute with here and here in S1, and it will give you -1 -1, the product is +1. But if you come here, it will anti-commute, it will kind of nothing will happen here for S2, but this one, it will anti-commute and it will give a -1 error, right? Fine with this. Now, then the question comes is that if you try this kind of thing, you will immediately see that, okay, it seems that I am able to correct two errors as well. So why are you calling this a single error correcting code? Because let's just double iterate this. If I have this XX error, the first case X anti-commutes with Z, second X anti-commutes with Z, two anti-commutation makes it commutation. -1 coming from first qubit, -1 coming from second qubit, they make it +1 again. But on S2, this one does nothing versus this one anti-commutes gives a -1, right? So now I can just say that, okay, but this S2 is giving me -1. So I am able to actually detect this error. Why are you telling this is a single error correcting code? The reason is, if you take, say, like this, you can sometimes show that it is able to correct more than one bit flip error. This is true. But if you come to phase flip error, right? If you come to phase flip error, let's say you have a phase flip here, it will anti-commute with this one. So you get a sign in the eigenvalue. But if you have another phase flip here, it will be unable to anti-commute. And you can check this anywhere. So when we say that an error correcting code can correct only a single error, it is possible to have that maybe it can correct more than one X error, maybe it can detect a bit more, maybe it can correct more than one phase error, but until and unless given any error, it is able to correct two of them, I cannot claim that it is an error correcting code which is correcting two errors. So what we see here, that there may be scenarios where it is able to detect more than one bit flip error, but it won't be able to do so for phase flip Z type errors. So it is a single error correcting code. It is not a two error correcting code. It cannot correct two errors, two or more errors. Now, the question here is that what probability or something like that, that it works? What should be the error probability so that I know this kind of scenario will work? Let's think of this. When will my short code work? So when will this QECC work? Simple. Either there is no error, then nothing to correct, or there is at most a single error, or at most a single error, right? So if we think of this, then what is the probability that this code fails? Let's look into the probability that this code fails. So we understand it will fail if there are two or more. What is the probability of that? What is the probability there is no error? It is 1 minus p to the power 9, where p is the probability of single error. So here p is the probability of single error. So 1 minus p to the power 9 is the probability that all the 9 qubits are not erroneous. What is the probability that one qubit is at most or exactly one qubit is erroneous? Well, one qubit is erroneous, rest of the 8 qubits are not erroneous. So it is p into 1 minus p. How many ways can this happen? It is 8 choose 1. Sorry, 9 choose 1. So I hope this is obvious. So what this basically means is that there are 9 qubits. Any one of the qubit, if it is erroneous, I'll be able to correct it. The rest of the 8 qubits should be non-erroneous. So the probability that one qubit is erroneous is p, and rest of the 8 qubits are non-erroneous is 1 to the power 8. How many ways one qubit can be erroneous? Out of those 9 qubits, I choose one. Essentially, 9 choose 1 is 9. But yeah, that is it. So this is actually the probability that the code doesn't fail, where the code works. So the probability that the code fails is this. 1 minus if there is no error and if there is only one error. If you work this out, roughly this will turn out to be 27p square plus order of p cube, higher order terms. So this code kind of fails in this way, right? This is the probability that the code fails. 27 times p square plus order of some more higher order terms. P square is the dominating term here. Now the point here is that let's take one code. Now you can ask that, okay, but how do I then correct for two errors? Maybe you can have of the short code that can correct two errors, doable. But you see the problem here. If you say that, okay, I have created a better version of short code for correcting two errors, I will say, what about three errors? If you say I have, okay, I have again gone back and created a better version of short code that can correct three errors using more qubits, I will say, what about four errors? So it is a never ending scenario that can keep going. You can start designing bigger and bigger codes with more and more qubits that can correct for more and more errors. But I can always say that, okay, you can correct t errors. What about t plus 1 errors? There is no ending to this. So one of the way which this is addressed is, let's say you have a single qubit. Let's consider it like this. A single qubit. This is a single qubit. Okay. What is the probability that, so it is a single qubit, no error correction, just the physical qubit. What is the probability that this qubit, if I compute with this one single qubit, it fails? The probability is p, is the probability of error. And since I have not done any error correction, if an error occurs, immediately everything goes wrong. There is no error correction. So what did we do for that? We added some redundancy. We encoded the information of a single qubit into multiple qubits. In case of shortcode, 9 qubits. So I am going to represent it like this, that I have encoded my information of a single qubit into multiple qubits. Here I am just using 3. Hello. Wait, is my screen visible?
Screen not visible, sir.
Okay, just a minute. Okay, I hope it is visible now. So here I am taking just 3 qubits just for the sake of clarity. If I just draw 9 qubits here, it will become very cumbersome. So this is the probability of failure. Okay. So I'm just taking 3 qubits just to make it less cumbersome, but you can consider like any n here. Now, what is the probability that when you have taken a qubit, encoded it into 3 qubits, let's consider the bit flip channel, we were encoding it into 3 qubits. What is the probability that this fails? It's in the order of p square. This is like order, okay? Order of p square. Now, what if I treat each one of these, I treat as a single physical qubit, they are single physical qubit, and then I encode it again using 3 qubits, each one of these. This one again this one. What is the probability that this one will fail? So this can correct a single error. This first layer, this say layer 1, this can correct a single error. If there are 2 errors, then this will fail. So this layer will be able to correct for 2 errors. So if there are 3 errors, it will fail. You can again take one of these and you can again concatenate into 3 and so on. And be able to basically correct more and more errors. So what am I doing here? A single qubit, I am encoding it into n qubits, n physical, one single physical qubit encoded into n physical qubits, which forms a logical qubit. Each one of those n physical qubits, I again encode it into n more physical qubits. So the number of physical qubit requires becomes n square. In the layer 3, it becomes n, so on. It keeps growing exponentially, right? But what is the nice thing here? So if I do that, what is the in layer 1, what is the probability of failure? It is some c times p square, where c is number of ways two errors can occur. Is two errors can occur. Here C was 27 for short code. For any code, I'm just taking it as C. And just mathematically, I can write it as 1 over C, C times P whole square, right? Now, if we go to layer 2, what happens? Now, instead of P, I have this CP. So the probability of failure will be 1 over C. Previously, probability of error was P and the probability of failure was Cp square. Here, probability of error is Cp square. So the probability of failure here will be Cp square square. If I go to layer 3, probability of failure is 1 over C, Cp whole cube 2 to the power 3, and like this. If I go to layer K, then my probability of failure is 1 over C, Cp 2 to the power K. Right? Now, if you look into this, I am expecting that, what is my expectation? As I start increasing the number of layers, my probability of failure should go down. Correct? So I am expecting that 1 over C Cp square is less than just P, probability of failure P, and this is less than 1 over C Cp square square, and so on. So as we keep increasing, I am expecting that my probability of error should go down. Otherwise, what is the point? When will this happen? Let's think. When is this going to happen? If you see, it will only happen, this happens when P is less than 1 over C. Why? When P is less than 1 over C, that means C times P is less than 1. So when you increase the power of that, something which is less than 1, it is getting smaller and smaller. Correct? So this happens only when P is less than 1 over C. Again, just reiterating, that is because C times P, which implies essentially C times P is less than 1. That means exponentiation makes it smaller and smaller. And you can understand, if my C times P is actually greater than 1, and if I start doing this, actually I will be increasing my probability of failure. I will not be decreasing. So if by any chance, if P is greater than 1 over C, then exponentiation exponentiation makes it bigger, error correction fails. Right? So this particular tipping point where P is equal to 1 over C, this is often denoted by PTH and called the threshold. So this is kind of the tipping point. If your probability of error, so you can understand this 1 over C depends on the choice of code. And your P is actually dependent on the hardware. Depends on hardware. So if your P, this value PTH, this is the threshold point, and only if your probability of error is less than threshold, only then this is this idea that we showed here. This is called concatenation. This idea is called concatenation. What is the beauty of this idea? Let's try to think, what is the beauty of this idea? You can always say that, but come on, you are just increasing the number of qubits exponentially. True, I agree. And this is one of the reasons you will realize that error correction is still not available today. And whenever we say that, oh, Shor algorithm, everything will require millions of physical qubits, now you understand why. Because as you start increasing the power of your error correction, the resource requirement starts increasing exponentially. True. So if you require n qubits here, you require n square qubits here, you require n cube qubits here, and so on. But if you look into the probability of failure going down, I am assuming that my probability of error is lower than the threshold. It is going down double exponentially. So while here resource increases exponentially, my probability of failure decreases double exponentially. So the this probability of failure goes down to zero very quickly. Of course, it is an exponential thing, so it will never be exactly zero, but you can always decide that, okay, I am willing to tolerate up to this much of noise. You take something very, very low, Today, around in classical systems, we have around 10 to the power minus 12 probability of error. So if you want to go to a very, very low probability of error, you decide what is the amount of error you are going to accept, and you can come up with the number of concatenating layers that you need for that. This entire idea that we saw, this is called the threshold theorem. And what this shows essentially is, now it is not a point that you can only correct one error or two error. You can correct arbitrarily many errors, as many as you want, if you properly choose your number of layers of concatenation. And the resource increase is exponential, but the reduction in the probability is double exponential. So it is kind of better balanced towards the reduction. This idea here that we discussed is called fault tolerance. You can tolerate your faults in the system. You have a scenario where everything, because what we just were showing here, let's come to this circuit that we created. What we didn't talk about very clearly is, when I am just saying that error can happen here in this part. I am just saying error can happen here, but these gates are also erroneous, right? When we discussed about this, we kind of assumed that all the gates are perfect. The channel here at this point is the only source of error, which is not true. All these gates are erroneous. So the question is that, how do you tolerate these errors? How do you create a more or less perfect system where each and every component is noisy? You do that by increasing redundancy with the way we just discussed here. And this is the idea of tolerating fault in the system. You have a system which is very noisy, where and you are trying to correct the noise in the system using some noisy components. And still, as long as you can satisfy this requirement, as long as you can satisfy this requirement, you will be able to achieve lower and lower errors by doing concatenation. This is the idea of fault tolerance. And if you recently see the Willow fit that Google came up with, and it created a lot of fuss in the scientific community, the reason was that they were able to show, they used the surface code, and they were able to reach a probability of error in the hardware which is less than the threshold of the surface code for the first time. That's what made uh, a very good chip when they were presenting it. Because what that means now is, if they are able to have a probability of error which is less than the threshold of the error correcting code that they are using, then you can actually use different techniques to take the error as low as possible by using these ideas of fault tolerance. Fine here. So this is one last thing here. I did a maths here and showed you what is the, that how do you calculate what is the probability that the code fails and all. Let's look into what is missing here. Okay, so I have, say, 9 qubits, q0, q1 up to q8. And what this says is, I am able to tolerate the fault, or I am able to correct up to a single error. What is the probability? Two error happens in 2 qubits, right? What it doesn't consider, so here will be the encoding part. If you think, this will be encoding. Then we have what we were calling as our noisy channel, followed by our syndrome extraction. Now, the moment we go for syndrome extraction, how many qubits will we need for syndrome extraction? Let's come back here and try to argue. Here we require 2 ancilla qubits for syndrome extraction, right? Why? because we had two stabilizers. Let's come back to the stabilizer formulation. We had two stabilizers. One ancilla qubit corresponds to one stabilizer. Here we have 8 stabilizers. That means I would require 8 ancilla qubits. So 8 ancilla qubits. Now, an error can occur during encoding, error can occur during the noisy channel, error can occur during the syndrome extraction, error can occur on these 8 ancilla qubits. Finally, when you do the measurements, even then error can occur. All these things that I am talking about is missing in this calculation. Therefore, it is very, very, very difficult to come up with the exact threshold of a particular error correcting code mathematically. Because all this is saying is there are 9 qubits and this channel is noisy. What is the probability that it throws in more noise? This is the only thing that this calculation is telling us. But all the things that goes into the play, the encoding part, the syndrome extraction part, the ancilla qubits, what happens if everything was perfect but error occurred in the ancilla qubit? Then also you get some incorrect outcome and you will wrongly think that the error is on the data qubit. That is not true. So what is usually done to calculate this kind of threshold is not this mathematics. You will see in many papers, usually threshold is calculated numerically. Calculated numerically by considering some noise channel, by considering some noise channel. In most of the papers, some noise channel. In most of the papers, you will see that they consider the state preparation and measurement error. They consider gate errors. And gate errors will be the unitary error that we were talking about. And state preparation or measurement error. So gate error can be any one of the Paulis. It can be I, X, Y, Z or some unitary, which is a combination of I, X, Y, Z. And state preparation or measurement, when we measure, it is just a classical type of error, right? I got 0, but I wrote it down 1. I got 1, but I wrote it down 0. So it is between identity and X. And so the thing that they do is they select an error correcting code, and this will be the probability of physical error, probability of physical error. This will be the probability of logical error. So logical error, what does it mean? It means that even after doing this correction, there is some error in your system. It can happen, right? This code can correct this calculation of short code. This can correct a single error. So even if you applied error correction, there can always be scenario where there is more than one error and therefore your system has your logical system, your encoded system still has some error even after you do error correction, because your error correcting code can correct up to one error and there was more than one error. So it can always happen. So this y-axis is the probability of logical error. What is the probability that even your encoded state becomes erroneous? When you don't do any error correction, it is essentially a straight a 45-degree line. If you don't do any error correction, your physical error is your logical error, because there is no logical qubit. You are not doing any encoding. It is like this scenario. It is the scenario here. It is there is only one qubit, and if there an error occurs, that itself is the logical error. So probability of physical error is the probability of logical error. But as you look into, as you do error correction, what will happen is typically your um, probability of physical error is usually lower than the probability of logical error up to some point. So say at this point, say this is your 45-degree curve. Let's assume this is my 45-degree curve, and this part actually tells me this part tells me error correction is useful. It is able to reduce the probability of logical error. Let's give it a red dot. It is able to reduce the probability of logical error up to this part, but if the probability of physical error becomes very high, then your error correction is not going to work, right? We already saw this, that it will work, at least in the ideal scenario, it will work as long as this kind of 27p square. So it will work only if p is less than 1 over 27 kind of thing, right? So now let's say that this is my d equal to 3 code. Okay, so you can design, say, a bigger short code using more qubits that will have a distance, say 5. If you have a higher distance code, it will start correcting more errors. So it will become something like this, right? If you take a, so this is, let's assume this is a d equal to 7 code, sorry, 5 code, d equal to 5 code. Now, if you take d equal to 7, it will even lower the probability of error, and it will retain the system, like the system will be having lower logical error probability than physical error probability. Let's assume that this is d equal to 7. But what happens is that at some point, these lines intersect. What does this mean? It means that you have reached a particular point of physical error probability where p is equal to the threshold. This is your exact PTH point. Now, beyond PTH, what will happen? What we saw here, if my probability of error is greater than my threshold, then actually doing concatenation fails. It induces more error. What it also means is that at this point where the probability of error is higher than the probability of error is higher than the threshold probability, if you increase the number of qubits, you are just increasing the space of putting more errors. It will be more erroneous. So the part that we were obtaining, that as you have d equal to 3, d equal to 5 is better than d equal to 3, d equal to 7 is better than d equal to 5, the code was getting better and better as you put in more resource, as you make the distance bigger and bigger. But beyond this particular point, it will flip. Now d equal to 3 will show a better performance than d equal to 5, which will show a better performance than d equal to 7. So numerically what is done, and numerically you take your code that you are interested in, short code, steam code, surface code, whatever that you are interested in, you start simulating the system with this kind of noise and put noise in everything that we discussed here. Encoding erroneous, channel erroneous, syndrome extraction erroneous, ancilla qubits erroneous, measurement erroneous. Everything you start putting noise, which gets almost impossible to capture mathematically as a single expression, but you can numerically create this plot, and you will get this tipping point, which will be your threshold probability. And usually this threshold is way lower than what this mathematical thing will give you. Why? Naturally, because it is easy to see that your mathematical calculation that we did here was actually taking a much more idealized scenario where many of these steps were noise free, which is not true in real life. What is usually seen is surface code and currently quantum LDPC code, low density parity check codes. They have the largest threshold, have the largest threshold which is around 1%. So they can tolerate around 1% noise. These two codes, surface code is used in Google's system, QLDPC codes are used in IBM's system, but QLDPC code has some extra benefit that it requires way lesser qubits for encoding compared to surface code. But anyway, these two codes have the largest threshold, which is 1%. Every other code that we are aware of has a lower threshold. That is why these two codes are way more interesting for the industry. One more thing I just wanted to, we have just 15 minutes and let me just cover and then we can stop for questions. What we saw here is shortcode and then all of these things, fault tolerance, how do you calculate threshold, mathematically, numerically, all of those. What this shortcode didn't really tell us, shortcode kind of, came out of blue. I just told you, see, this is how things happen. It came out of blue. It didn't come through a very, there is a very rich classical error correcting code theory. I didn't utilize any of those to calculate or to generate shortcode. It just came out of blue. So after that, there was a scientist called Steen. He came up with the Steen code. And what his approach was is very interesting. So Steen code actually showed, there was also another question that in classical error correcting repetition code, we saw that we need 3 bits to correct a single error. But short code gave us 9 qubits to correct a single error. Can we do any better? Right? So Steen came up with an answer with that. Let's look into classical error correcting code. What happens in classical error correcting code? We have two main things. One is the G, which is the generator matrix, M, which is the code word, or no, this is the message. Sorry. M is the message. And let's say my message is 1 cross K. Usually the message is written as a row vector. And then my generator matrix will be K cross N. And my code word C is equal to M times G. So essentially we have a 1 cross N, the code word. So what it means, K bits are encoded into N greater than K bits. So what this is telling me, K bits are encoded into N greater than K bits. How that encoding happens is controlled by the generator matrix. If you know the generator matrix for a given code, you know everything about that code. Now, after your computation, say computation is my noisy channel. After my noisy channel, I end up with some code word C tilde, which may be noisy, which may not be noisy. I don't know. So I have another matrix called H, which is the parity check matrix. The parity check matrix H. And H times C, what this gives me is equal to S, which is called the syndrome again. So the syndrome name comes from classical error correcting code. If my S is all zero, so this is a zero vector. If my S is all zero, it implies no error otherwise. So if you look into, this is kind of the, in a very short or in a very quick sense, this is kind of the what the formulation of any classical error correcting code is about. You have some message, which is some 1 cross K bits. You have some generator matrix, that is a k cross n, which takes a message and maps it into a 1 cross n system, which is the code word. And finally, you have the parity check matrix. The parity check matrix can actually be created from the generator matrix. When you apply the parity check matrix on the code word, it gives us the syndrome. If the syndrome is 0, that implies there is no error. If the syndrome is something else, it implies there has been some error. So let's look into the very famous Hamming code. Hamming code is a 743 code. Sorry. Remember NKD 743? It's a 743 code. So this is N. 4 bits are encoded into N 7 bits that can correct a single error. So it's a 743 code. If we look into the generator matrix of this, usually, so this is 1 0 0 0 0 1 0 0 0 1 0 0 0 0 1 1 1 0 1 1 0 1 1 0 1 1 1. This is the generator matrix for the Hamming code. And you can easily see this is how we can actually create the generator matrix, that this portion is my identity and this portion is the parity portion. It creates this parity portion creates some linear combination of the code words or the message in some sense to create the extra redundant bits. And this first part is essentially the identity. It keeps the bit as it is. So it is actually appending some parity to the each message. Now from here we can construct what is called the parity check matrix, right? So this was my identity. This was my, sorry. Yeah, this was my identity. This was my parity check part P. My parity check matrix H will be P transpose times identity. This will be my, this is just by definition. So that's why I said that if you know the generator matrix, you know everything about the code, or even the other way around. If I tell you the parity check matrix, you know everything about the code, because from the generator matrix you can create the parity check matrix, or if I give you the parity check matrix, you can create the generator matrix. So what will be my parity check matrix here? So my parity check matrix for this will be 1 1 0 1. Sorry, this is my P transpose. So it is 1 1 0 1 1 0 1 1 0 1 1 1. So this is my P transpose part, and I have my remaining part as my identity 0 1 0. So what Steam did, so this was already well known. This was already well known. I mean, we all have perhaps studied Hamming code before. What Steam did is Steam showed that how can you take a classical error correcting code and create a quantum code out of that. So the idea is whenever you have 1, you replace that with Z. Whenever you have 0, you replace that with I. This will construct stabilizer. So what will be my stabilizer for this? I will have Z, Z, I, Z. This is my stabilizer 1, Z, I. My stabilizer 2 is Z, Z, sorry, Z2 is Z, I, Z, Z, I, Z, I, and my stabilizer 3 is I, Z, 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 I, Z. Now it's a 7 bits, so there will be 7 qubits. That I need 6 stabilizers. These 3 stabilizers, which are formed using only I and Z, they can correct for bit flip error. And similarly, I can write X, X, I, X, X, I, S5, X, I, X, X, I, X, I, S6, I, X, 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 I, X. This will correct for phase flip. These 6 together forms the stabilizer for what is called as the Steen code, which is a 713 code. Once more, remember classically it was 743 code. It was 743 code. But here you can again very easily show that you single error. You cannot correct more than one error. Therefore, it becomes a 713 code, and you can just take 1 qubit information and map that into 7 qubits. It's a 713 code. But what this paper, why this paper is very nice, is it shows you how to take a classical error correcting code and construct a quantum error correcting code from that. There is a bit more to it. What this says is, this is something following this paper. There was another paper by someone called Calderbank, Calderbank, Shaw, Steen. They came up with a more mathematical background on how to create codes, and these are called CSS codes. The idea is you take some classical error correcting code C1. This is some classic error correcting code. From its parity check matrix, you create the stabilizer. Create stabilizers. That is what we did here. But you should note one thing. From the parity check matrix, I was able to go up to this S1, S2, S3. I kind of repeated the same for S4, S5, S6. Is that allowed? So what they showed is you take C2, create stabilizers, say I and Z. You take some other error code or the same error correcting code. Another classical error correcting code. And from its parity check matrix, from its parity check matrix create stabilizers using I and X. And if C1 is a what? Okay, sorry, I don't know what happened here suddenly. So maybe I can see. Okay, just give me a second. It seems like the screen froze. Yeah, sorry, the screen froze somehow, and it seems some of the writings were gone. But I hope you already saw the writings. So, not repeating the entire writing, it will take some time. So, from C1, the idea was you create the stabilizers using identity and Z. From C2, you create the stabilizers where C1 and C2 are just some classical error correcting codes, and you are creating the stabilizers from the parity check matrix like this. And if C1 is a subset of C2 orthogonal, then the stabilizers are guaranteed to commute. For Steam code, C1 and C2 code, and it still hold this condition. Therefore, we end up with stabilizers created from only the same codes and they commute with each other. But this is kind of the construction of the CSS code that shows that you can take any two classical error correcting codes, ensure that for those codes this condition is guaranteed or this condition is satisfied, and then from the parity check matrix of one of the codes create the stabilizers including only identity and Z. From the parity check matrix of the other QEC classical error correcting code, create the stabilizers using identity and X. And these stabilizers are guaranteed to commute with each other. So now you have a set of stabilizers, say from for Steam code, what we saw S1, S2, S3, it can correct X error. And we have S4, S5, S6, which can correct Z error. So by construction, CSS code ensures that your number of by construction, your CSS code ensures that the stabilizer correcting X error and the stabilizers which are correcting Z error, they are different. They can be partitioned into two sets. So these kind of codes are very easy to construct. The shortcode, steam code, surface code, all of these satisfy this CSS code construction. But I'm sorry, I'll just take maybe 2 or 3, maximum five minutes more. But it is also possible to come up with codes which are non-CSS. And this was the Steam code was this 713 code. So it can correct a single qubit error. It can encode 1 qubit into 7 qubits, which is better than Shor's 9 qubit. But the question still remains is whether we can go up to the 3 bits that was used in classical. There is another quote from Laflamme, which is a 513 code, and this is a non-CSS code. So if you look into its stabilizers, since it's 5 qubits, there will be 4 stabilizers. So this is I, X, Z, X, X, I, X, Z, Z. You can perhaps realize that there is kind of a cyclic shift between the stabilizers. And this you can see is a non-CSS construction. The X and Z stabilizers are not partitioned into two different sets. So this is a non-CSS construction. And if you try to implement the error correcting circuit for this kind of non-CSS codes, they tend to be so much more resource hungry. You need so much more resource for this. I did some studies like this during my masters, and what would have required, say, 50 gates for Steen code would require around 3000 gates for Laflamme codes. That is the amount of resource increment that happens. Therefore, you will see that in practice, where non-CSS codes are very interesting mathematical concepts that we can look into, but in practice, non-CSS codes are not applied. If you read Laflamme's paper, you will see how they found this error correcting code. They have straight out written that they have run a brute force simulation on a computer, and the computer has come up with this set of, by running every possible combinations on 5 qubits, they have come up with this set of stabilizers. So one last question here is, how did you know that you have to search on 5 qubits? I said that they have written in their paper that just by running every possible combinations of 4 stabilizers using 5 qubits cases, for a 5 qubit QECC, they were able to find this 4 uh, stabilizers. There is no mathematical beauty behind this. But the one last question is, how did they know that they need to search for 5 qubit codes? And this is where things come. So let's suppose I have an n qubit QECC. What is the total size of the Hilbert space for this? It is 2 to the power n. This is the total size of the Hilbert space. That means the dimension is 2 to the power n. That is the, there are 2 to the power n. What, like let's, I'm, but these are important. Dimension is 2 to the power n. That means there are 2 to the power n orthogonal directions in this space. That means each of the 2 to the power n cases, I can distinguish between them because they are orthogonal to each other, right? Now, let's say that what is the total number of errors that can happen? X, Y, Z on each qubit. This is the type of errors that can happen. These are the errors, right? Identity is not an error. So X, Y, Z are the errors. Just give me a second. So X, Y, Z are the errors that can happen on each qubit. So if there are n qubits, there are 3n possible errors. Now, one last thing that can happen is the case where there is no error. That means identity on all qubits. Mind, XYZ, if it happens on any one qubit, that is. If identity happens on all qubits, that is no error. This is the no error case. So total possibility is 3n plus 1. I don't know why the screen sharing is stopping. So there are 3n plus 1 possible cases. Now you have 0 logical, you have 1 logical, correct? So for each of these 0 logical, 1 logical, there are 3n plus 1 possible combinations. So there are 2 into 3n plus 1 possible errors. Now, each of these errors, if I am claiming I can correct these errors must be orthogonal to each other. If these errors are orthogonal to each other, only then I can do a measurement and distinguish between them. If they are not orthogonal, I cannot distinguish between them. What is the total number of orthogonal dimensions in a in qubit QECC? 2 to the power n. So we need to satisfy this condition. This total number of orthogonal errors that I am trying to identify must be less than or equal to the total orthogonal spaces which are dimensions which are available in my Hilbert space. And if you solve for this inequality, n will turn out to be greater than or equal to 5. So the smallest QECC that we can have in quantum is a 5 qubit QECC. We cannot have 3 qubit QECC in quantum. The minimum number of qubits you need is 5. And that's why Laflamme's code is the optimal error correcting code that is possible in quantum computing. But it's a non-CSS code and it has many disadvantages there. However, mathematically speaking, this has a importance because it is the smallest error correcting code possible. And this paper also shows this very nice calculation. How do you come up with this in the minimum number of qubits which are required? So I'll stop here. I have already taken 10 minutes more. I'll just stop here.
Thank you, Ritaji sir, uh, for this extra session that you have taken and also patiently responding all the queries and all the questions. It was wonderful. And if anyone has any query, they can always contact later on to sir, or even you can write to ftp.academy.united.ac.in, so we can forward it. Thank you so much, sir.
Thank you. Thank you for allowing me this extra time.
So, good afternoon, everyone. Once again, now we are going to have another session by Jayakumar sir. In I think in 1 or 2 minutes we can start. Sir, are you there? Good
Yes,
afternoon,
sir,
sir.
I am there. Am I audible? Am I audible?
Yes, sir. You are audible. So,
We'll
before
give,
starting,
yeah,
let me
we'll give break.
quickly introduce Jayakumar sir. Yes, sir.
We'll give 5 minutes break, sir, because they are attending from 2 o'clock.
Yes, sir.
Fine, sir,
Okay.
fine, sir.
So okay, that's fine. So we can have a 5 minute break, and we'll join again at 3:17, 3:18 around. So we'll start by 3:18. After 5 minutes, you can take a break.
Fine, sir, fine.
Okay, so welcome you all. Uh, I hope we can start. So let me introduce uh, Jay Kumar sir to you. So he is a founder and CEO of Anatantra Private Limited, and he is also serving as a recognized IBM quantum educator for so many years. And with MNIT, he is associated with last, I think, last 1 year, sir, or before that.
1 year, sir. 1 year.
Yes, sir, last 1 year. And participants always enjoy your sessions. And once again, today he is going to give you simulations, experiments on various algorithms on quantum computing. So I wholeheartedly welcome you, sir, for today's session.
Thank you, sir.
And without taking much time, I think I'll let me handle it to you and let me uh, share to you. So it's over to you, sir.
Thank you,
You
sir.
can
Thank you so much.
continue
So,
the session.
good afternoon to all. It's my immense pleasure to rejoin with you. Let me share my screen. I hope my screen is visible to you.
Yes, sir, visible.
Okay. So today we're going to cover about quantum algorithm. First, we'll cover the basic concept. I quickly refresh what is the quantum algorithm. Then we go for simulation. Okay. To understand quantum algorithm, we need to understand each and every process happening inside quantum computing is like wave interference. So each and every operation happens inside quantum computer. It is like an interference of multiple waves. So quantum algorithm uses a global property of the values in the qubit to change their amplitude. So what we are doing in quantum algorithm, we try to manipulate the amplitude of our particular preferred signals. Okay. So there are two fundamental goals in quantum algorithm. One is for reducing the amplitude of wrong answer, and one is for increasing the amplitude of correct answer. So if you are doing any quantum operation, any quantum experiment, you will have multiple kind of results. So your results will comprises both correct answer as well as wrong answer, and you don't know which one is correct, which one is wrong. To do that, we need to run for multiple times. So if you are running for multiple times, then you are doing measurement, then you get high probability with the correct answer. So this is the basic about quantum algorithm. So today's session we're going to cover Dodge-Joshua algorithm and Groover's algorithm. So Dodge-Joshua I will cover in very quick manner because this is theoretical part. So it is like quick refresh. So Dodge-Joshua problem always related to the problem who am I? So a function is given to you and you don't know what type of function it is. A function is given f of x something. A function have input 0 or 1. A function will produce 0 or 1. Okay. So what is the basic task? And you need to identify what type of function it is, whether the function is constant or balanced, you need to identify. So how will you able to identify? By giving your input, by checking the output produced by that function. Okay. So this is how we need to do. So the basic question is the given function is constant or balanced. So for that, whatever the input you are giving for your function, if it is always produce 0, I'll take pointer. If it is always produce 0, then it is a constant function. So whatever you are giving the input, if your function always produce 1, then you can classify it as a constant function. Okay. So if we are giving any input, if it is giving x for the first iteration, and the same input or different input, if you are giving the opposite output of previous iteration, then you can determine the given function is equally balanced function. So based upon the output, you can determine whether it is constant or balanced. So classically, how will you do? Classically, we will give some input. take an example of f of 0. So you're giving 0 as the input and you're getting 0 as the output, and you cannot determine this function is a constant function. Okay, so we need to verify our function with different input. So case f of 1 equal to 0, it means the both time you got the same output. It means the given function is constant. By varying your input, you got the same output. Okay, so look at the third line, f of 0 equal to 1. It means you are giving 0 as the input and you got 1 as the output. And we cannot determine what type of function it is. So what we are doing, we are giving one more input, f of 1. Now you got output as 1. Then you can be able to conclude this is a constant function. Okay, so alternatively, if you are looking at right side, so if you are giving 0 as the input, f of 0 equal to 0, it means you cannot determine what type of function it is. So for the same function, what you are doing, you are varying your input. So f of 1 equal to 1 means it is contradicting the previous output. So if you are able to get this catch, then you can determine it is a balanced function. So what type of balanced function? Equally balanced function. Right. So similarly, if you want to know if your function is constant or balanced, at least you need to run twice in your classical system. So this is the best possible way we can able to identify the given function. But in case of quantum, you can build an oracle. So oracle will give you what type of function it is. So for a single run. Okay, so this is the major comparison between classical and quantum. So in classical, you need to run twice, but in quantum, you need to run only one time, single time. Okay, this is the good advantage if you want to compare classical and quantum, because for single input, it is not a big deal. For multiple input, for 100 input, for 1000 input, for million input, for billion input, within a single run, you're able to identify whether the given function is constant or balanced. So he proposed this algorithm in 1985 called quantum church theory, proposed by David Joyce. That is why this algorithm name is David Joyce problem. So what is the important part of this algorithm? We have two qubits. So x starting from state 0, y starting from state 1. Okay, we are having two qubits, and one qubit is actual input. The second qubit is additional qubit, ancilla qubit or helper qubit. Okay, what we are doing, we are applying Hadamard gate. I hope everybody know the operation of Hadamard gate. Okay, from 0, if you apply Hadamard gate, you will get positive state over here. You'll get positive state over here. From 1, if you're applying Hadamard gate, you will get negative state. So recall these fundamentals. These are very important. So we are giving these two inputs states to the given function. We don't know what type of function it is. So this function is black box. It will appear like a black box. You don't know what is the type of that function. Okay, you need to give input and you need to observe your output. By doing that, you need to determine whether it is the constant function or balanced function. Then what you're doing, your function with reacting with your input. So it will react with positive state, it will react with positive state, and it will react with negative state. According to your function type, you will get different output. Okay, so here you will have output and you are applying Hadamard gate, and after that you are doing measurement. So your measurement will give binary value. Your measurement will give binary value. So always remember, you have binary value. So we have binary value. We are encoding to the given qubits. So we are encoding to the given qubits, and we are preparing quantum states. So binary value 0 means we are preparing in state 0. Okay. So binary value 1 means we are preparing in quantum state 1. So remember this. So we are starting from binary value and we are doing all quantum operation. Finally, we are doing measurement. After measurement, you will get binary value again. So quantum circuit reads from left to right. So this is the way this circuit will get executed. From left to right, it will do operation one by one sequentially. Okay. So what is the input qubit? X. What is the value? X equal to 0. It means state 0. Helper qubit Y equal to 1. It means it is a binary input. Now what we are doing, we are applying Hadamard gate. We are applying Hadamard gate. So here you can see we are applying Hadamard gate to both of them. Then it will create equal superposition. It will set them in equal superposition. It means the function will give f will returns 0 if it is a constant, 1 if it is a balance. So what it means, your output is 0. Imagine your output is 0. Okay, binary value is 0. That is why I mentioned with double quotes. It means whatever happens over Hadamard gate, you should reach state 0 over here. It means you need to have positive state. So from positive state, if you apply Hadamard, you'll get state 0. Okay. So when you will get positive state, if your function is constant, Okay. So in other case, I'll try to change the color. Okay. So we'll get binary value 1. You'll get binary value 1 if it is balanced. So when you get balanced, before doing measurement, it need to have state 1. So before Hadamard, you need to reach negative state. Your function will produce positive state if it is constant. Okay, if your function will create negative state if it is balanced. Then only if you apply Hadamard gate, you will get state 0, you will get state 1. So recall all these ideas. Okay, so in a single measurement, you are able to identify the given function is constant or balanced. So this is the beauty about Dodge-Josh algorithm. Okay, I will repeat, no issue. So all of you imagine you are starting from stage 0. Okay. Then if you are applying Hadamard gate, what you'll get? You'll get positive state. Okay. From positive state, if you are applying Hadamard gate, you'll get stage 0. Suppose if your function is constant, it will react with positive state and negative state, but here it will yield only positive state. From positive state, you look at the second law. What happens from positive state? If you are applying Hadamard gate, you get stage 0. From stage 0, if you are doing measurement, you get binary value 0. Okay. In the second case, if your function is balanced, okay. So if our function is balanced, it will create negative state over here. From negative state, if we apply Hadamard, so what it will produce? It will produce state 1. So here you'll get state 1. From state 1, if you are doing measurement, you'll get binary value 1. So just like the previous law, from state 1, if you're applying Hadamard gate, it will create negative state. So it is vice versa. So recall all these basics. So that is why I am refreshing all this stuff before going for simulation. So you need to implement, thank you, sir. You need to implement 4 options. So f of x equal to 0, f of x equal to 1, f of x equal to x, f of x equal to not of x. So we have 4 different possibilities. Okay, your function will produce state x and state y XOR with f of x. So here we are using XOR operation because the same input means it will give some output. The different input means it will give a different output. Okay, so case 1, f of x equal to 0, it means You are giving two inputs. So X is your actual input. Okay. So Y is your additional input, additional qubit you can say. So X is actual qubit. X is actual qubit. So you're giving two different inputs. So 0 and 1. But what is the output you're going to generate? This is your function. So what is your function? Your function is f of x equal to 0. F of x equal to 0. So take y value as it is 1, do XOR with f of x. What is the f of x value? 0. So 1 XOR with 0, you'll get 1 because both inputs are different. Both inputs are different. If both inputs are different means if you do XOR, you will get 1 as the output. You'll get 1 as the output. Okay. So do for the second case. Here y is 1, XOR with f of x. XOR with f of x. What is the value of f of x? 0. You get 1. So for both cases, first and second case, you will get 1 as the output. So look at the third case. Look at the third case. 0, 0. So here the value of y is 0. What is the value of f of x? 0. Okay. So 0 XOR with 0, you'll get 0 because both inputs are same. If both inputs are same, it will yield 0. It will yield 0. Okay. So look at the fourth case. 1, 0. So 0 XOR with 0. 0 XOR with 0 will get 0. So I hope everybody able to understand XOR gate. So the circuit is whatever you give for X, it will retain as it is, no change. Okay. So whatever you give for Y, it will react with f of x equal to 0. So this is the circuit relationship. So this is the circuit relationship. Second case, f of x equal to 1. So case 1 and case 2 are constant function. So both cases will happen for constant function. Okay. So take an example of first possibility, x equal to 0, y equal to 1. We are using XOR gate only. So look at the input. So what is the input of y? Input of y is 1. And what we are doing XOR with f of x equal to 1. So what is the value of f of x? 1. So 1 XOR with 1, you'll get 0. Same input. Same input. Okay. So look at the second case, second combination, 1, 1. So you need to focus only on y. You need to focus only on y. So 1 XOR with what is the f of x? 1. You'll get 0. If you understand first, you can be able to understand the second case. Okay. So do for the third one. Now the y value is 0. XOR with f of x equal to 1. So 0 XOR with 1, you'll get 1. 0 XOR with 1, you'll get 1. Okay. So look simultaneously four possible combination 1, 0. So 0 XOR with 1, you'll get 1. So if you go for circuit relaxation, this is a simple NOT gate of case 1 output. So look at here. Look at here. If you're adding a NOT gate over here, so 1 will turn into 0. Okay. This 1 is also going to turn into 0. This 0 is going to turn as 1. This 0 is going to turn as 1. So if you're adding NOT gate for your output, you are able to get the case 1 output as it is. Okay. So case 1 and case 2 are differentiable. You're able to see the output case. So you're able to see the output case. Okay. Case 1 output and case 2 output are differentiable. So within a single glance, you're able to differentiate case 1 and case 2. So both are equal to constant function output. XOR is different gates, exactly. XOR is different gate. If you're giving same input 0 0, it will give 0. Okay, if you are giving same input, it will give 0. But if your output differs 0 1 or 1 0, it will yield 1. So in last session, Redajit beautifully had parity check. Parity check. I will recall parity check. So what is the meaning of parity check? Whether the same input, whatever the same input they transmitted, you able to receive as the same output. Okay, same way we able to check. Whether the inputs are same, it will give 0. If input differs, it will give 1. So this will help you to identify error correction. Okay, within the sender and receiver have the same data. If you do the simple XOR, you're able to get same idea, nothing different. Okay, so next, case 3 balanced. So here it is a little tricky part. So what you do, you need to do XOR with X with Y. So what is f of x? F of x is nothing but x. So do XOR with 0, XOR with y, it will give 1 because inputs are different. Inputs are different. So here you can consider x as it is, y as it is, and you need to do XOR with x and y. XOR with x and y. So if you have pen and paper, you can work out. You can work out. So this is the circuit realization. So this is equal to C not gate, control not gate. So all of us know control not gate, we revised multiple times. So even though I will revise one more time. So whenever there is a control in X, whenever there is a control in X, it will do not operation of your Y. Okay. So whenever there is a control in X, it will do not operation about your Y. Otherwise, it will retain as it is. It will retain as it is. So it will differ. So whenever there is a not operation, I represented with this red color. Okay. If there is 0 in X, it will retain Y as it is. It won't change. So this is an example for control now. So case 4, f of x equal to not of x. It means what is supposed to do? What is supposed to do? You need to take x dash. So what is the x dash of x? 1. Okay. So 1 XOR with 1. 1 XOR with 1. The inputs are same, you'll get 0. So you need to create one more column called x dash and do XOR with x dash and y, and you will get output. So these are very basics. So if you have doubt, please work out in pen and paper. You will easily able to get. So this appears like reverse CNOT. This appears like reverse CNOT. So like case 1 and case 2, like case 1 and case 2, if you are doing not operation for your case 3, okay, you'll get case 4 output. Example, 1 turn into 0, okay, 0 turn into 1, and 0 turn into 1, 0 turn into 1, and 1 turn into 0. Okay, so case 3 and case 4 are differentiable. By looking at this output, you're able to differentiate whether it is the output of case 3 or output of case 4. But if you look all these tables, all four outputs are differentiable, different pattern. Okay. So in a single view, you're able to identify what type of function output it belongs to, whether it is a constant or balanced. By looking at the output table, you're able to determine. So quantum use this property. So we'll go for detailed explanation. So we have two qubits. One is actual qubit, another one is helper qubit. We apply for given function. Okay, then we apply Hadamard gate in first qubit. Then we do measurement. So mathematically, if you look, So two inputs, if you do tensor between these two, so one will yield to positive state, one will yield to negative state. Okay, if you have the combined view, you have this state. If you have combined view, you will have this state. Okay, so so this is state 0. This is positive state. So this is 1. I will denote this belongs to 1. Okay, so this is state 1. So after Hadamard, you'll get negative state. Negative state means 2. So this belongs to state 2. State 2. Okay, so this is the combined form of this equation. You can mention like this. This is the combined form. Okay, so this combined state will go through your function, and what is happening? It will happen for different combination. So entirely 1 by root 2 multiplied with all these combination state. So what is the four possible combination for 2 qubits? For four possible combination, state 0 0, okay, state 0 1, state 1 0, and state 1 1. These are 4 possible combination for 2 qubits. You can notice over here. You can notice over here. Okay, so look at the function constant. Now we combine f of 0, f of 1 equal to 1. There is 0. So we can pull the common terms out. So state 0 plus state 1 multiplied with state 0 minus state 1. Okay. So same way you can do for f of 0 and f of 1 equal to 1 for constant. I will share this material. Please go through it. And you'll have only one output called a sign difference. In first case, you have positive. In second case, you have negative. So remaining everything is same. Remaining everything is same. Right. So next, for balanced, you'll have minus 1. For the another balanced, you'll have minus. So some changes are there. Some changes are there. You need to notice the change. For constant, you'll have positive. For constant 1, you'll have negative. For balanced, you'll have minus 1. For another balance, you have just minus sign. So if you do measurement, it will have 2 branches. If you do measurement, it will have 2 branches. Okay. So for constant function, this is the term you will have. It will go to positive state. For constant, if your function is constant, as we discussed earlier, it will go to positive state. Okay. From positive state, if you apply Hadamard, it will goes to state 0. Okay. So from positive, if you apply Hadamard, it will go to state 0. Or balanced, I'll choose the same color. I'll choose the same color. For balanced, it will go to negative state. From negative, if you apply Hadamard gate, it will go to state 1. From state 1, if you do measurement, either it will get 0 or 1 based upon your function. Okay. So all this theory they covered in previous lecture. So you can notice the entire Dawes algorithm in case of multiplied with minus 1 to the power f of x. So if measurement returns 0, it means it is a constant function. Okay. So this is the equation. Your function going to react with positive state. I'll change color. Your function going to react with your positive state and it will yield this term. So now substitute two possibility. So what are the two possibility? F of 0 and also f of 1. If you apply this value, we'll get positive state. Okay. In same way, if you do for balanced, what is the meaning of balance? The output of f of 0 will not be equal for f of 1. So each time it will contradict. Each time it will get contradict. Okay. So if you apply in the same equation, it will go for negative state. it will go for negative state. So this is the simplest explanation of Dodge-Josh algorithm. We covered theory part in very quick way. Now we can go for simulation. Okay, so for that so all of you go for IBM quantum platform. I'll share this link to you. So today we're going to cover about IBM Qiskit platform. There is no real-time application of identifying constant function or balanced function, but it will prove quantum algorithms are superior in nature. So in classical, you need to run twice. In quantum, you need to run only one time. So all of you go to this link. If you are very new to IBM Qiskit, all of you go to this link. Is my screen visible? Is my link visible, accessible in the chat box? So please look at your chat box. Okay. So
Yes,
please
sir,
go to
Vijay.
that. Yes, sir. Please go to that link. So click sign in. Click sign in. So to create an IBM account, you need to have credit card. So if you have credit card, please create an account. So this is very worthful. They will charge if you go beyond the use. For 1 minute, they will charge 9,000 rupees. So you need to be very careful if you're using IBM Qiskit. So without login also, you're able to use this domain, but you cannot execute a real quantum system. So maybe in future in Andhra Pradesh, in Amravati, if they set up real quantum system, we might get access. But even though for that, we need to have credit card. So credit card is for verification purpose. So now they are strict, little bit applying stringent rules. So come to this login. The dashboard will look like this. So click here, top right. Yes, these. So it's up to you. You can select any region. So by default, they will give US and also German if you're accessing from India. Okay. So you can click learning tab. So all of you click learning tab. So even without login, you're able to access this. So don't worry about the login. If you don't have credit card, don't worry. For studying purpose, we actually no need of access of real hardware. Okay, even simulator is more than enough. So go to this link, second link I share. So if you come down, you can see view all modules. I'll share the last link also, view all modules. So go to view all modules, scroll down, and you can see Josh algorithm. So click that module, So go to this page. I hope everybody able to launch this page, Josh algorithm. So whatever we covered previous session, we're going to implement through simulation. Okay, here you can notice what are the components you need to have. Qiskit version 2.1, Qiskit IBM runtime, Qiskit AER, Qiskit visualization, NumPy, and LaTeX. So all these components you need to have. So this algorithm don't have any real use case, but it will prove quantum supremacy. Okay. So whether this dark theme is okay, shall I move to light theme? Which one is preferable? So please put in chat box, dark theme or light theme. Okay, dark is okay. Yeah, I will make it slow. Don't worry about the practice session. So here you can notice whatever we discussed in previous, we able to observe over here. If f of x equal to 0, if f of x equal to 0, if your function f of 1 always produce 0, then it is a constant function. It is a constant function. If f of x equal to 1, if you are giving f of x equal to 1, if your function f of 1 always produce 0, it means it is a constant function. Constant function. So this is how you can understand. By giving your input, you can check your function. The function f of 1 is constant, which always produce 0. Which always produce 0. So look at f of x equal to 2, f of x equal to 0. For the second case we are looking at. Okay. So here what happens, if you are giving 0 for f of 2, if it produce 0, you cannot decide what type of function it is. So you need to vary your input 1. Then if your f of 2 always produce 1, it means it is contradicting. So for 0 it produce 0, for 1 it produce 1. It means it is a balanced function. It is a balance. So the first one is constant, the second one is balanced. Okay. So look, f of 3. Look at the f of 3. Now we are in f of 3. Okay. Now we are in f of 3. For f of 3, if you are giving 0, if it produce 1, you cannot determine. So now you are changing your input. You are giving 1, and if your f of 3 is producing 0, it is contradicting. So each and every time your output contradicts to previous one. It means this also belongs to balanced. Now look at case 4, f of x equal to 0. If you are giving 0, if it produce 0, now we are changing f of x equal to 1. Then if it is producing 1, it means both are same output. Same output means it belongs to constant. So whatever we covered in previous slide, so we have different version. We have different version. So this is very simplified version. This is very simplified version. For f of 1 and f of 4, it is a constant. It is a constant. Okay. But for f of 2 and f of 3, but f of 2 and f of 3, it is a balanced function. It is a balanced function. Okay. So this is the theory we covered. Okay. Now, so this is the general layout of your Josh algorithm. So you have input qubit state x, and you have additional qubit state y. And what is the function u of f? Okay, you don't know what type of function it is. And what this function will generate, it will generate two outputs. So state x, state y XOR with f of x. So this is what we discussed in previous session. Okay, if we scroll down, this is your coding part. This is your coding part. Okay, so you can download this code by clicking over here, download notebook. So all of you click this link. All of you click this link. Download notebook. Download notebook. And check it your download. Check it your download. Check it your download. So you'll have .joshua ipynb. So this is the file you need to work on. So if you have Google folder, so if you have notebook, Yeah, it will not open. It will not open. Don't worry. Don't. So it is a interactive Python notebook. So note down this stuff. So IPYNB means interactive Python notebook. Interactive Python notebook. To execute this, what you're supposed to do, you need to go to this website, QBreak. So all of you go to this website. Looking for chat box. Okay. So all of you go to this website, QBreak.com. So this QBreak.com will give a simulation platform. If you want to do some quantum coding, so this will help you. This will help you. So go to this website, sign up. So if you have Gmail account, you can do sign up. I already created login. So once you created login, you will have this dashboard, launch lab. Okay. So click default workspace, click next. So all of you able to get the launch lab. Select free 2V CPU 4 GB RAM. So click launch lab. So after this, what you do? Click default workspace. Free CPU version 2, right? Like this. So it will launch lab. So do slowly. If you're able to get this launch lab, let me know. So it is equivalent to Jupyter Notebook or Google Colab. You can imagine like this. So once lab is ready, it will automatically launch like Jupyter Notebook kind of environment. So whatever discussed in that website, the same code you are able to upload. So how to upload? So click here, file, new, and you are able to open from the path. So click open from the path. Otherwise, what do you do? Click here, upload files. Click upload files. I'll put in the chat box. So once you're able to log in, upload file icon. So click upload files and select Joshua IPUNB file. Click open. Click open. So once you do, you will get the same file over here. So if anybody uploaded, please put in the chat box. I'll mention step by step. So you can copy my commands and you can put in notepad for your understanding. Okay. So here, what you can do, we can run this command. So initially it is uncommented. So now you can remove this hash and you can run comment in this way. Yeah, it will take little time. You need to wait for some time. So don't worry about that. Once you're able to run this command, you'll get messages like this, collecting Qiskit information. It will automatically install the latest file. If you're able to install, successfully, okay, after this, you'll get this notification. So wait for some time, and let me know, are you able to install successfully? If anybody installed up to this, please put in the chat box. Okay, sir. Very good, sir. Always active. Anybody else? I will wait. No worry. Okay, very good, sir. Once you completed installation, what you can do, you can restart your kernel. So note down all these points. So go to kernel, okay, restart kernel. Go to kernel menu, select restart kernel. So this is the way you can do. Suppose if you don't have Qiskit version 2 like me, so here you can see I got Qiskit version 2. If you don't have this version, what you can do, you can select environment. So click environment. So all of you click environment. So if you don't have this environment, what you can do, click environment. So click environment. Okay. So click add, click add. Click add. You can search biscuit. You can search biscuit. So under biscuit, you can select options. So select biscuit version 2.2.3. Select biscuit. Search for biscuit. Select 2.2. Select biscuit version 2.2.3. So this is the latest version. So try to install latest version. So select this. Click install. Click install. So all of you able to install version 2.2.3. So it will take some time. It will take some time. So what is the good thing about this QBraid lab? QBraid lab, you can install any kind of quantum platforms. So you can install Penny Lane, you can install Microsoft, you can install IonQ, okay, Classic. So major quantum player platforms you are able to install in QBraid. So no need to switch. So even though if you have older version of Qiskit code, you can run over here. You can run over here. So there are 4 patterns applicable for a Qiskit software. So before that, I will write what is the meaning of Qiskit. So Qiskit stands for Quantum Information Science Toolkit. Quantum Information Science Toolkit. So it is a framework. It is a framework built by IBM. So it will give a platform to do simulation and real-time execution about quantum circuits. So you can do both. You can do simulation as well as you can do real execution. Okay. Suppose if some packages are missing, you can select your kernel over here. You can select Python 3 Qiskit version 2. So do like this. Select and give start. Then what you do? Go to kernel, restart kernel. So whenever you update any kernel, so you need to do like this. Python file no need to share, sir. Here, if you go to this link, go to this link. So go to this link. I will share in the chat box. You can download that file. You can download that file. So look at here, download notebook. So look at here, download notebook. Maybe I try to get link of this address. I'll put in chat box. So this is the file location. So if you click this, it will directly download. Okay. So if it is not clear, what I will do, I'll close, I'll do from the basic, I'll do from the basic, I'll do logout, I'll do once again. So if you are very new for this domain, I can understand you are not able to follow. Okay, once you created login, you can log in with your Gmail account. So most of us have Gmail account. So once you logged in, okay, you can go for launch lab. You can go for launch lab. Okay, so it will come default workspace. I hope everybody able to follow. Click default workspace, click next. So it will come free 2 version CPU 4 GB RAM. So what you do, if it is not started, you can restart. It will come like this. So click launch lab, click launch lab. So lab is ready. It will automatically open. Lab is ready. It will automatically open. Yeah. Okay. So what I do, I'll clear workspace. So whatever the file I am having in previous session, everything is clear. So this is how your environment look like. Okay. So what you do, so click environment. So select add environment. So here browse about QuizKit. Okay. So it will come. So select this. So I already installed 2 environment. So click QuizKit version 2.2.3, which is latest version. So before running any code, you need to check what are the requests. So here what it is mentioned, version 2.1.0. Okay, here also it is mentioned version 2.1.0 or newer. So it should not be less than that version. So make sure. Okay. So try to click here, try to install. So click install. So once it is installed, you can see over here. So once it is installed, click this refresh button. So click this refresh button. Okay. I install QuizKit 2.2.1. In your case, it could be 2.2.3. Okay. So click here, new folder. So say demo 1. So you can give your name. So click here, click new folder, give some name, Okay. So click here. So you downloaded that file, right? .josha.ipynb. So click that file. File is getted. File is uploaded over here. Click here. Now what you do after uploading your file, click here. You can select your kernel. So click whatever the kernel you install. Click select button. After uploading ipynb file, okay, go to kernel option, select this related kernel. So here you can change your kernel. Okay, if you click here, you can change your kernel. So I'll draw over here. Here you can see. Still, if you are not able to follow, don't worry. This recorded video is there. Whenever you got doubt, you can go to this video. You can recheck. Okay. So once you uploaded the file, you can come down. You can install one by one. So here you uncomment, you run in this way. So once it is installed, what you can do, refresh, go to kernel, restart kernel. So uncomment the first line, like this. Execute in this way. So it will start from exclamation mark, then pip followed by the install command. So it will install all prerequisite dependency packages. So once you install, go to kernel, select restart kernel option. So after successful installation, go to kernel menu, select restart kernel. So scroll down. Once it is installed, okay, you need to copy your credentials over here. In the instance, you need to copy. So in actual file, there is no instance, right? So go here, you can see in actual file, there is no instance. So here you can notice, instance equal to your IBM instance CRN. Okay. So these detail available from your login. Once you successfully logged in using your credit card, these informations are available. I'll show you where it is available. I can show you. So this is where you can find your CRN value. So in your dashboard, here you can find CRN value. Okay. So what you're supposed to do is supposed to copy this value. You're supposed to copy this value. So click this. It will copy your CRN value. It will copy your CRN value. So come to this file, click here and paste. So I cannot show my value to you. It is confidential. Okay, do at your end. Once you have successfully logged in your IBM ID, okay, CRN value will get generated. Okay, so you need to copy from that location. All of you able to follow? If you created account, please do that. Otherwise, don't worry. Otherwise, don't worry. If you don't have credit card, if you not yet created login, don't worry. Anybody able to paste? Put in the chat box. Anybody successfully pasted their CRN value? In this file, in the instance. Are you able to log in, sir? Are you able to log in like me? Are you able to see your name? So once you have successfully logged in using your credit card, you'll get this value. It means you are not able to create your login. If you create a login, it will come under your name. Okay, a CRN value is generated for. Okay, so click here, it will copy your CRN value. Go to your file, see this IPUNB file where you uploaded. So click here, instance equal to, click here and paste within the single quotes. Okay, fine. So next, you have token. Okay, I cannot show. I'm not supposed to show. Okay. So for token, click here, API key, click create. Click create, give some name. Give some name. So what is the next step? You need to click CRN value, copy that, paste in the code where CRN equal to within single quotes. Okay. So next what you do, look for API key. Look for API key. Okay. Click create plus. Click create plus. Give some name. Give some name for API. Click create. So it will create API value. It will create API value. So if you click view all, you can see. So I created API key for this demo purpose. So if I click here, I can see details. I can see details. I can copy that key value. I can copy that key value. So here I can copy that key value. So copy this key value. I'm not supposed to show. You need to paste in this way. You need to paste that API token within single quotes. Paste that API token where for look like token equal to within single quotes. So run this, and you can check what are the server backend available for you. What are the server backend available for you? Okay. To understand what are the backends available for you, you need to click here. You need to click here. Okay. So go to your login. Go to your login. Click compute resources. To check available quantum computers, available quantum computers in your login, go to menu, select compute resources. So please go through chat box. So whatever I'm mentioning, please copy paste in Notepad. I will share this detail after this session. Don't worry. So see over here. Okay. So whatever you look over here like lock, it means you cannot access. Okay. So these three quantum computer I am able to access. So IBM FEZ, IBM Marrakesh, IBM Torino. So these three quantum computer I am able to access. So for you it will be different or it could be same. It could be same. And look at the capacity 156 qubit system, 156, 133. So each and every quantum computer have different purpose. So if you're looking at pending jobs, so you need to select the least amount of pending jobs. So in my case, I selected IBM Torino because the pending job is only 3. Okay. The more number of pending jobs are there, more time it will take. Okay. In my case, I selected IBM Torino. So go to your coding, and give like this. So whichever the computer is least busy, you need to mention that computer. So this is the name of quantum computer. Okay, IBM Torino I put. So what I'm doing, I about to run this code. So once again, I need to rerun all this code. Yes, it took a lot of time. Okay, once I installed, what I do, I'll go for kernel, I will restart kernel. Then only you'll get that environment. Now I pasted CRN value, I pasted API key value. If I start to run, it will show what is the backend selected through server. So I got IBM Torino. So if you are not able to get this output, it means you are not able to access the real quantum system. So anybody got output like this? Anybody got output like this? IBM Torino or any other system? Please put in the chat box. So for me, 3 systems are available. For you, it may be different. Anybody got output? Please put in the chat box. Nobody able to run? Take your time. Take your time. What about Sendil sir, Lakshmana, Lakshmi Narasimhan Rao sir? Kopusamy sir, are you able to execute? Anybody got output like this? Okay, very good. Rosha Durgesh executed, very good. Only one. Okay, very good, sir. Then we can proceed. If 1 or 2 participants able to do, then the code is working. So here you can see, very good, very good. So here you can see the code. Okay. Now what we are doing, go to view, show line numbers. So it will be easy for you to follow what I am talking about. So line number 2, we are importing Biscuit runtime service from this library. Okay, line number 5, what we are doing, we are creating a sampler. We are importing a sampler. So many ways you can do sampling in Biscuit. So this is one version, version 2. Okay. So line number 7, what we are doing, we try to save our account. So each and every time if you access a real quantum system, you need to save your account. So for that, you need to have 2 inputs. One is instance value, CRN number. One is your API key value. So without these 2, you cannot access real quantum system. So once you have this information, you can save your account. So multiple times you can work on that system. Okay. So once you save that account detail, you're able to create quantum platform using channel. Okay. So this will give quantum service for you. So line number 9, it will create quantum service for you. So next you need to avail that service. You need to avail that service. For that you need to executing line number 12. So what we are doing, we are calling that runtime service. We are calling IBM Qiskit quantum runtime service. Okay. So in background, you need to pick some quantum hardware, some quantum computer. So for that, I picked IBM Torino. So likewise, you can select multiple quantum system according to your credentials. So you need to check this resource. So you need to go to IBM Quantum. So like this, you need to go to IBM Quantum. You need to click here. You need to click Compute Resources. So if you click Compute Resources, you'll get the idea. So what I will do, I'll share this link also. I'll share this link also. So if you don't know by that procedure, you can go through this link also. So this is how you need to access your quantum hardware. Okay. So once you got this output, you can confirm. Then you can go for samplers. Okay. So look at line number 2 over here. Look at line number 2 over here. from Qiskit primitives, import backend sampler. So we are importing backend sampler. Okay. For that, we need to have some noise model generation. So we are importing AER simulator and noise model. So here we are doing simulation, right? Quantum simulation. So what type of model you can select from different backend? You can select from different backend. So already we mentioned the backend. Okay. From that we are providing noise model. Yes, you can use the same code in Google Colab also. What is the advantage over here? You can install multiple versions. Okay. So try to execute all this code in Google Colab, which will easily you will get easy output. Okay, very good. Very good. So look at line number 14. Here we are mentioning noise model. So whatever the default model we are importing from this backend, we are importing over here. So same way we are importing sampler module, sampler simulation in line number 15. Okay. So we need a simulator as we need a sampler also. We imported both of them. Okay. So this is for real quantum system. This is for real quantum system. Suppose if you are doing a simulator, not going to access the real quantum system, then you can enable line number 18 and 19. So remember, if you are not able to use the real quantum system, you can go for line number 18 and 19. You can uncomment them like this. You can uncomment them. Okay. So note down this method. If you are not using a real quantum system, you can use line number 18 and 19. So run this code. Run this code. Now we got two things. One is AER simulator and backend sampler. Okay, once you executed some code, you can see the difference over here. So if it is black color solid circle, it means it is being executed. If it is executed, you can see gray color. You can see gray color. Now come down to cell 7. Come down to cell 7. So this is step number 1. Now you are mapping your quantum problem to your circuit. Okay. So here we are creating quantum circuit. So line number 3, what we are doing, we are creating quantum circuit. For that we are importing a library. Okay. So line number 5, it will call a quantum function. So line number 5, this is a quantum function. This is a function call. This is a function call. So for this function call, we have input. So what is the input? We are giving 2. So 2 means we are creating 2 qubits. This is the meaning. So note down. So line number 5, we are doing a function call. What is a function call? Quantum circuit is a function call. Okay, for that we are giving input 2. So if you are giving 3, it will create 3 qubit quantum circuit. So this function call, yes. So without having credit card, you cannot run actual quantum system. Okay. So if you do a function call, it will create quantum circuit, which is called QC. Line number 8, what we are doing, we are creating a function. We are defining a function. So line number 8 is function definition in Python. So what we are defining a function which contains a integer input. So integer input could be in 4 categories. So you can see over here. Okay. So you can give value 1 or value 2 or value 3 or value 4. So this is your input. Okay. So if your input is apart from this value, it will create a error message. It will raise a error message. Okay. So there are 4 inputs you can give, either 1, 2, 3 or 4. So look at your code. Look at your code. So what we discussed over here, we have only 4 functions. Okay, we have only 4 functions. So this is for 0, this is for 1, this is for 2, and this is for 3. Okay. So 1, 2, 3, 4, 3, 4. So depends upon your input, it will select your function type. Depends upon your input, it will select your function type. So remember this. Remember this. Okay. So if you are selecting 2, 3, it will create control not for your function. Okay. If you are selecting 3, 4, it will create a NOT gate. So Cx belongs to control not, X belongs to NOT gate. Next what it will do, it will create a Hadamard gate. It will put in Q0. It will put in Q0. I hope everybody know this code. Everybody know what is H, what is Cx, what is X. Is it clear, or I need to teach one more time? All of you know this code, basic code. Okay. So line number 27, what it will do, it will create a Hadamard. I need to tell once. Okay, no issue. So go to your login. Click Composer. So all of you go to this link. Even if you don't know, if you don't have login, you can go for this web page. So all of you go to this web page. So here you can notice 4 quantum bits, 4 classical bits. So here you can notice 4 quantum bits, 4 classical bits. So click Q0, select bin button. Click Q0, select bin button. So click C4, select minus. Click C3, select minus. So it contains 2 quantum bits, 2 classical bits. It contains 2 quantum bits, 2 classical bits. So I will select brighter theme. You can notice over here 2 quantum bits, 2 classical bits. So modify in this way. Now what they mentioned, QC.H0, it means you are implementing Hadamard gate in Q0. You're implementing Hadamard gate in Q0. So click here, you can get Qiskit code. Are you able to get the same code over here? Are you able to see? So circuit.H, Q register 0. So here the quantum circuit is named as circuit. Okay, in our code, the quantum circuit is named as QC. So look at the difference. Line number 5, what we are doing, quantum circuit 2, it means it will create 2 qubits. Okay, what is the name of the quantum circuit? QC. Come here. So what we are doing, QC.H0 means we are implementing Hadamard gate in Q0. We are doing composer in the same way. So we are implementing Hadamard gate in quantum register Q0. Okay. So look at the next code, QC.barrier. So in this output, you can see barrier over here. Okay. So what is the barrier? How to implement barrier in composer? So click here. You can see this 3-dot barrier. Select and place. So barrier implemented for single qubit. So click here. Go for edit. Enable Q1 also. You can implement barrier for 2 qubits. So whatever we covered over here by code, you can do step by step over here. So look at the code change. Circuit.barrier Q0, Q1. Okay, we are doing the same thing over here. So next what we are doing a compose function. So QC compose 2 qubit function 2. Okay, in place equal to true. It means by default, we are giving the value as 2. So check your input. What is the value of 2? So it will create control NOT gate. So case 2, it will create control NOT gate between 0 and 1. So between 2 qubits, it will create control NOT gate. So this is what happened over here, right? So this is what happened over here. Because you gave input as 2, it created control NOT gate. So how you do the same thing in the circuit? Okay, drag and drop control NOT gate, drag and drop control NOT gate. Okay, so place barrier over here, place barrier over here, and extend to Q1 also. So we did step by step. So if you look right hand side, you can see coding also. You can see coding also. All of you able to do so? All of you able to do so? So next what we did, we measured all. So QC measure all. So in Composer, how will you do? You need to do one by one. So drag and drop measurement in Q0, drag and drop measurement in Q1. Now you got output. The same circuit is generated using coding. That's all. That is the difference. So look at your code. What is the function given for here? So quantum circuit case is 2. So if you are giving 2 or 3, it will create control NOT gate. So next thing is transpile. Next thing is transpile. So here I will run this code. It means whatever the code you generated, I need to run this first. If I run this next, I'll get transpilation. So step 2, it will do transpile of the code what I generated, okay, according to the quantum computer architecture. So this is the circuit we created, right? So this is the circuit we created. But when you do transpile, this circuit will translate it into actual quantum computer architecture. I'll show how it look like. So go to the composer, home. I'll go to workloads. So this is the circuit I executed in quantum system. This is the circuit I executed. So in Qiskit, it will look like this. But if you do transpile, the same circuit automatically converted into this version. So this is an example for transpilation. So look at the circuit. So this circuit, one Hadamard control NOT gate, 2 measurement gate is converted into this form. Anybody able to see and look like this? Able to run? So after transpile, what you can do, you can run that algorithm in real quantum computer. Run this, and go for visualization. Run this, you'll get the output. Now we can see the appearance. It is get executed. So you need to wait for some time. Because I try to execute in real hardware, it will take some time. I can check over here. I can click over here. We'll go back. See, I submitted a job over here. Now it is showing in pending status. So once that quantum computer is ready, my job is get executed and I will get result over there. So sometimes it will take 5 minutes, sometimes it will take 2 hours, sometimes it will take 1 or 2 days. So depends upon the queue length, depends upon the priority, it will get executed. So I will stop it here. I will stop it here. So if you have any doubt until this, you can ask me. A very good question, Senthil sir, because if you select 2 qubits, you're going to execute in a full quantum system. A full quantum system will give access for 153 qubits. So you cannot use only 2 qubits. Okay, you need to implement the entire circuit for 153 qubit system. So in transpilation, your circuit is changed according to the quantum hardware. So that is the reason. Suppose if you have a bus, okay, bus have seating capacity of 54 seats, but only 5 passengers are there. But we need to take the entire bus, right? The same idea. You cannot enter program in IBM Qiskit. See, I will share that slide. This is only for graphical interface. So you cannot edit program over here. So whatever you are asking over here, I can understand. This is read-only mode. You cannot edit coding over here. You cannot edit coding over here. Okay. For coding, please try to use QBreak or Google Colab. That is the best possible way. So what is the tool I am showing over there? Composer only for your understanding, graphical understanding purpose. You cannot do coding over there. Good question. Good question. So try to execute until this step. We will cover the continuation part tomorrow, same time. You can draw in Qiskit and you can use a latex extension. It will create latex quality output for you. So in tomorrow we'll discuss how to create a latex format for a Qiskit circuit or output.
Thank you so much, sir, for this wonderful session.
Thank you, sir.
Uh,
Thank you.
Thanks to all the participants. Tomorrow we will meet at same time, 3 to 5. Okay, thank you, sir. Thank you so much.
Ma'am, code is available in this link. If you go to modules, IBM Qiskit module, you can get that code. Don't worry about that. Thank you all. Thank you. So if you go to that link, you can download that notebook.